Today we will explore the quantum description of optical fields through the lens of quantum field theory. Let's start with the vector potential operator of optical fields. The vector potential operator, denoted by a hat of RT, can be expressed as A0 times the exponential of I times k dot r minus omega t times a hat, plus A0 star times the exponential of negative I times k dot r minus omega t times a hat dagger. Here, A0 represents the complex vector potential, which is orthogonal to the wave vector k, and omega is the angular frequency. Moving forward, let's discuss the fundamental components of quantum optics, the annihilation and creation operators. The operator a hat annihilates a photon in the state n, resulting in the square root of n times the state n minus 1. Conversely, the operator a hat dagger creates a photon, resulting in the square root of n plus 1 times the state n plus 1. The number operator, denoted n hat, is defined as a hat dagger times a hat. We can also derive the electrical and magnetic field operators from the vector potential. The electrical field operator E hat of RT is defined as I times omega times the difference between A0 times the exponential of I times k dot r minus omega t times a hat and A0 star times the exponential of negative I times k dot r minus omega t times a hat dagger. The magnetic field operator B hat of RT is I times k cross the difference between A0 times the exponential of I times k dot r minus omega t times a hat and A0 star times the exponential of negative I times k dot r minus omega t times a hat dagger. Next, we consider the Hamiltonian and how it influences the time evolution of our system. The Hamiltonian H hat, representing the field energy, is 1/2 times h bar times omega times the sum of a hat dagger times a hat, which simplifies to h bar times omega times the sum of n hat plus 1/2. The time evolution of any operator a hat of t is governed by I times h bar times the derivative of a hat of t with respect to t equals the commutator of a hat of t with h hat. It results in a hat of t equals the exponential of I times h hat times t over h bar times a hat of 0 times the exponential of negative I times h hat times t over h bar, describing how the electrical field operator evolves over time. Let us delve into the specific time evolution of the optical field operators. The electrical field operator E hat of RT evolves as the exponential of I times h hat times t over h bar times E hat of R, 0 times the exponential of negative I times h hat times t over h bar. Simplifying the description using the annihilation operator A hat of t, which evolves as A hat times the exponential of negative I times omega t, where express the electrical and magnetic field operators, E hat of RT becomes negative E times the sum of x hat times sine of k dot r minus omega t plus p hat times cosine of k dot r minus omega t. Finally, let's discuss the quadrature operators, which are essential for understanding the properties of quantum fields. The quadrature operators, x hat and p hat, are defined as the square root of h bar over 2 times sumga times the sum of a hat plus a hat dagger for x hat, and 1 over I times the square root of h bar times omega over 2 times the difference between a hat and a hat dagger for p hat over 2. These operators, satisfying the commutation relation of I times h bar, mirror the classic position and momentum operators, highlighting the non-classical nature of quantum states through the uncertainty relation delta x hat times delta p hat greater than or equal to h bar.